Hello and welcome back. Today we're going to be talking about geometry and the geometry standards that are covered in the 7th grade. First thing we're going to talk about are scale drawings. Scale drawings are models that are used to represent items that are too large or too small to be drawn or built to actual size. One of the things that you might think of first of all is a house. Obviously we don't have drawings the size of houses on paper. That would be a little obscene, so we make scale drawings of them. And in this scale drawing that we're looking at here, 2 inches on the drawing is equal to 5 feet on the house. So for every 2 inches that we see over here, we have 5 feet on the house. And sometimes they're nice whole numbers, and you could just say, oh, well, there's 8 inches over here, and how many feet would that be over there? But this time we have 8.5. So you need another example of how to solve that. So we always compare the model to the original in fractional form, and every fraction is a division problem. But when I have equivalent fractions, I can solve them using a proportion method. So in this case, I'm going to cross multiply. This is what I don't know. I don't know how many feet are going to be in my real house in terms of its height, but I do know that on my model that it's 8.5 inches. So I'm going to take and I'm going to cross multiply and then divide. So I'm going to go 2 times x, which is what I've done here, 5 times 8.5, and I get 2x equals 42.5. I then divide by 2 because 2 divided by 2 gives me 1. And I'm trying to get this x all by itself to solve for x. And when I divide the other side by 2, because it's an equation, whenever I do to one side, I do the other side, I get 21 and 25 hundredths feet, or 21 and 1/4 of a foot. And that would be the actual height of our house, which now it makes much more sense that we obviously could not fit 21 and 1/4 of a foot on a piece of paper. So it's important that we're able to do these things, and at one point in time we're all going to live in a house. We might need to know how to do that and how to look at those types of drawings. We can also be told things such as the scale factor. If I have my smaller triangle and I'm trying to get to my larger one, we might look at it in a more basic way, that I can say that the scale factor from one triangle to the other is 2. So every side is 2 times its corresponding side on the larger triangle here. So if I start out, my smaller triangle, or my model is, or my original rather, is 8, and I'm multiplying that to get to my model, and my model must have a length of 16 then. And I'm going to multiply each side by the same amount so that my scale keeps my triangles in proportion, so that my triangle looks exactly the same except that it's larger. So my angle sizes are all the same. It's just that my side lengths are a bit longer. Now I can also talk about that, and I can compare the lengths and widths of an object, or a rectangle in this course, in this case rather, and I can look at how does that affect its area. So the width of my smaller rectangle is 2, and the width of my larger rectangle is 8. So I'm comparing the two widths. So I have a 2:8 ratio there. And my lengths of my rectangles are 6:24, and the smaller one being the 6 and the larger one being the 24. When I use these to find the area of the smaller one, I get 6 times 2, so 6 centimeters times 2 centimeters equals 12 centimeters. With my larger rectangle, I have 24 times 8, 24 centimeters times 8 centimeters, and that gives me 192 square centimeters. Now, my scale up here, you notice I'm either multiplying by 4, if I'm going from the smaller to the larger, I'd be multiplying by 4, and if I'm going this way, I'd be multiplying by 1/4, which you can also think of as dividing by 4. And the same can be said down here. I'm either multiplying by 1/4 going back, or dividing by 4. But you notice down here that doesn't quite work out. So what we find is that I have made this into little squares. I have squared it. And so the scale factor is also going to be squared. So since this was 4 up here, I'm going to square it, and my scale factor down here is 16. Or if I'm going back the other way, I would be multiplying by 1/16 or dividing by 16. One of the other topics we have in geometry is it really a triangle? And instead of having a drawing for us, a lot of times they just have measurements. And when I'm talking about the interior angles, in other words, the angles inside the triangle, I need them to equal a total of 180 degrees. So the three, I can divide them up however I want, as long as their sum, their total, is 180 degrees. And you can see in these three examples that they do indeed all add up to be 180 degrees. So these are actual triangles that we could construct. If they don't equal 180 degrees, either my triangle is collapsing in on itself, or one of the angles is too big and it won't make a match to the other side, and we would have an open triangle, so it would just be a three-sided open figure. So in order to make sure that it is a true triangle, we have to do that angle measure test that it does equal 180 degrees. I can also use this if I have a triangle and I have the 180 and I have two of the angles, I can find that third angle. And you'll see them do this a lot of times, where instead of the number for the measure of the angle, they have some sort of algebraic expression, x plus 30 or 2x minus 2, and you have to set it up as an equation. Know that you can add the other two, subtract them from 180, set that up into an equation, and that you can then solve for that. Another way to tell if a triangle is really a triangle is I can do a test of its side lengths. And the way that I look at this is any of the two side lengths, when added together, their sum should be greater than that third side, that remaining side. So if I take a look at this first one, I've actually gone over here and I've drawn this triangle. And it says that my side C was 5, so I made that my shorter side, and I made a scalene triangle here. All three sides are different. A is 7 and B is 10, so B was my longest, second longest, shortest. So if I add A and B together, the 7 and the 10, are those greater than 5? Well, indeed, 17 is greater than 5. When I check my next set, A plus C, 7 plus 5 is 12, and 12 is indeed greater than 10, which is the length of that third side. The last test I need to do then is the last two sides. The B plus C is greater than A. And when I check that, 10 plus 5 is 15, and that is indeed greater than 7. A lot of times where they'll catch up on here is that the two shorter sides will not be greater than the longest side, and that's usually the one where they'll throw in that little glitch for you that it's not really a triangle. And what happens if those sides aren't long enough, the triangle ends up collapsing down on itself, and instead of even having this little tiny bit of area, they end up being flat lines on top of each other. And a lot of times if the A and the two shorter sides are not longer, I end up with two lines like this. And that was my longest side. That's my two shortest sides put together. And it's impossible for them to meet and at the other ends there to connect. Talking of three-dimensional shapes, one other geometry concept that we're going to cover is that we have cross-sections. In other words, I take these three-dimensional shapes and I start slicing them, basically. You think of it like, Fruit Ninja. When you slice the fruit, what shape are you seeing on the inside? So if something cone-shaped came down and I cut across the top, my shape on the inside wouldn't be this pointy thing anymore. I would just have circles. My rectangular pyramid here, when I cut across, I don't end up with a pyramid shape anymore. I end up with the rectangles, the shape of the base. Same thing if it's a square pyramid, I end up with the shape of the base when I cut directly across in a nice horizontal cut. If I have like a can of Coke shape, a cylinder, and I cut across it, well, when I look inside, I'm looking at a circular shape. If it's a rectangular prism and I cut across, I end up with a rectangular shape. When I do a cross-section of this cone here, and instead of cutting across, I cut straight down, when I open it up, the shape that I get is actually a triangle. So it is thinking of these three-dimensional shapes, like I said, with Fruit Ninja, which is a game I know my kids like to play, and thinking of what shape you will see when you cut into that three-dimensional shape. Next concept that we're going to talk about is the circumference of a circle and how to find that. And first we need to know that this is a radius. It goes halfway across the circle. And this is the diameter. It goes all the way across the circle. And if I have the radius, I can multiply it by 2 to find the diameter. And conversely, if I have the diameter, I can divide it by 2 to find the radius. So we have two different formulas here that we can think of. We can always, though, go back and forth between diameter and circumference simply by multiplying and dividing by 2. So I can think of the circumference as pi times the diameter, Or because the diameter is 2 times the radius, I can think of the circumference as 2 times the radius times pi. So in this first one, it's just 3.14, which is an accepted value that can be used in place of pi. It's a rounded estimated figure. And when I multiply those two items together, I'm going to get a distance. It's a distance around the circle. So circumference is the distance or the perimeter around the circle. And you can see these different problems. You're more than welcome to pause it and try to figure out where we got the numbers from and work through those problems on your calculator. But we're again using pi as 3.14 in this case. There's also a lot of times on your calculator a pi button. And if it asks you for it to be exact, you can leave it just as pi. So I could have left this one right here as 4 pi. So if I'm doing it in terms of pi, that would be 4 pi. This one would be 23 pi. And those could be my exact answers, as these are actually estimated answers and not completely equivalent, because 3.14 is simply an estimation or a rounding of pi. I'm also going to need to know how to find the area of a circle, and the area is the space inside of the circle. It doesn't have nice straight edges, so I can't just multiply and make little squares inside. If I were to cut this into little squares, I'd have pieces and parts of squares with rounded edges. It wouldn't work out well. So a formula was derived, and pi is actually going to be used again, and pi is a ratio that tells us if this is the diameter, is 10 meters in this case, I could take that and wrap that diameter around, and it would take a little bit more than 3. And so that ratio, that division problem, is what they keep going on and on to try to figure out what does pi perfectly equal. Do we ever have a stopping point? Since we don't, we usually round it, like I said, to this 3.14. In this case, I'm using the radius squared. My radius here is 2. Now over here, remember, I have to take the diameter and divide it by 2 to get the radius. So in this case, I had to do 10 divided by 2 to get the 5. Over here, I already have the radius, so I can just plug it in. And whatever that radius is, I'm going to square it and then multiply it times pi. In this case, we're using the figure 3.14. So I invite you to pause this video and try these out on your calculator just to see how that works and see if you get the same answers. Our next topic are complementary and supplementary angles. Complementary angles, when added together, equal 90 degrees exactly. So I could have two angles that don't add up to 90 degrees. That might add up to 80 degrees or 75 or 62. If they don't add up to exactly 90 degrees, then they are not considered complementary angles. This is helpful because if I know that this is a complementary angles to each other, and I know one angle measure but not the other, I can always subtract that from 90 to find the missing angle measure. Supplementary angles are very much the same, only instead of adding up to 90, they add up to 180, which is also a straight line. That's also the angle measure of a straight line. So if I have a straight line sitting there like that, to measure the degrees from here to here, that is 180 degrees. And the right angles are the ones that are perfectly an L shape there and have, you'll see them demonstrated with this little square in the corner to show that they are indeed right angles. So supplementary angles must add up to 180. So if they don't add up to exactly 180 degrees, the two angles, then they are not supplementary angles. So these are pairs of angles that add up to 90 degrees and pairs of angles that add up to 180 degrees. The other types of angles we're going to talk about are vertical and adjacent angles. And I apologize, some small writing over there. Vertical angles are directly across from each other. And the neat thing about this is if I have straight lines that are intersecting, as long as they are both straight lines, the angles that are directly across from each other are going to be exactly the same measure. They're going to be congruent in that way. So if this angle is 134, its vertical angle is also 134. This becomes helpful because you'll have problems with a whole bunch of angles and you're trying to figure out which ones are which. And I can look at these two right here, they're on a straight line, and those could equal 180, so I could use my supplementary angles, but I could also use my vertical angles. If this one is 46 also, this one across from it is 46, so it's not just up and down, it's side to side. So I have to look at my angles very carefully. Now, adjacent angles are angles that are simply next to each other. They don't need to add up to any specific sum. They are just next to each other. Sometimes adjacent angles are supplementary angles. Sometimes adjacent angles are complementary angles, but they do not have to be. Those are just some examples of this vocabulary in use.